right, it's time to take a look at friction. So normally if I was in class, we would do this, but you can do this at home. It's a pretty easy demonstration. If you have a flat edge surface like a ruler and three different size coins and you push them all so that they fall off the table at the same time, you will find they should all hit the ground at the same time because they're roughly the same surface area. So fluid friction isn't going to be an issue here. And obviously we're going to start talking about friction. And remember, everything falls at 9.8 meters per second squared. So all three of those should actually hit the ground at exactly the same time. And the reason why it doesn't always appear that way is because air resistance, fluid friction, can slow things down, and that's called that terminal velocity. So in a vacuum chamber, I can drop ostrich feathers and a bowling ball in the same time, and they will hit the ground at the same time in the absence of air. And if you look at the front of this folder, I have a GIF of that, where an ostrich feathers and a bowling ball are dropped within this huge rocket vacuum chamber, and they hit the ground at the same time. So if you have a chance, go ahead and try that. You'll see that that should happen. So friction is any force that opposes motion. Irregularities on two surfaces get caught on each other, and from the force from one surface exerts on the other is called friction. So when you rub your hands together, you will experience friction. Your hands will warm up. The byproduct is that from that energy is heat. You have fingerprints because that causes an irregular surface so that we don't drop things when we go to pick them up. So friction acts in the opposite direction of the object's motion. So friction opposes motion. If I apply friction force this way, forward, then my frictional force is backwards. So friction will cause an object to come to a stop. If you're an ice skater, you know this. You turn, if you're a hockey player, you don't have toe picks, or you're a figure skater and you're cooler at skating than I ever was. You literally jump to your side and use the side of your blades to create more surface area, more friction to slow you down. So the strength of force of friction depends on two factors. Basically, the type of surface involved and how hard those surfaces push against each other. So if I am a skier, I'm reducing my friction, but if I am the reindeer up there, I want my hooves to have a lot of friction to give me the ability to push off the snow in this case. But the skiers want to be behind them without so much friction because they want to slide easily behind. And there are three types of friction. And as it snows this time of year, this is when we start having issues with sliding friction. And I'm not going to turn the volume on because we're getting into copyright because it's set to Slip Sliding Away by Paul Simon. So you can go watch it if you want to hear the music at the same time. But the point is, snow can have an issue where we have trouble with rolling friction with tires and we go into sliding friction, which means you don't have a lot of control. So this car, by the way, brakes on ice is guaranteed to send you out of control pretty much. You're better off to as you start to drive, you'll learn how to turn into or out of a skid or a spin, depending on if you have front wheel or rear wheel drive. I tend to put my car into four-wheel drive when it gets bad out, but four-wheel drive doesn't mean go as fast as you want, because the second you hit your brakes, a four-wheel drive car acts just like any other car and you can have trouble. By the way, trying to open your car door and stop your car from sliding does not work. The safest place you can be at that point, for the most point, is just in your car and hope that no one else gets you. But in this case, that's a 4-car pileup. But they managed to get out, get some friction back, and get some rolling friction. I think this is the same one. They showed it twice. Got that one, other car moving too. So as this goes on, they have a lot more options, and it gets funnier and funnier. Let's go past this one. See the next one. You tried to use the curb to stop, and that did work. They happened to get some ability to steer. This one is sliding, and they're about to hit that car in front of them, and that's a chain reaction. Here comes the next one. this person is trying desperately and they're going sideways. This one's trying to get out to stop the car. Well, that's really stupid. Because now that person's about to get hit because the car behind him is sliding and he just gets out of the way in time. So again, this is not going to slow down your car. You are not going to reduce the friction. You're not going to increase your friction enough to overcome the loss of frictional rolling. Let's go to another one. Maybe. Well, hopefully that's in there, and if you want to go back and see more sliding friction, go for it. Rolling friction is exactly what we're talking about. Literally, if you put wheels under your skates, you have rollerblades. In fact, you can have inline skates. My neighbor is actually the one that invented the inline skates. So I know that person. I grew up next to him. Well, actually, it was one street over. So rolling friction is just that. You put bars underneath there and roll a heavy block. That's how we think a lot of the pyramids were used, was with some rolling friction. And they've had demonstrations where they've moved super heavy blocks using big tree trunks to roll it, or other things that were around to roll it. Now we use metal pipes because we can make sure they're even, more evenly.
How does drinking heavy make you feel?
I'll get rid of that. This was a commercial, but it was one of the first CGI commercials, and this is an old one, and it was for Avion. I'm not endorsing that, but I think this is the funniest thing. So we have babies roller skating. So this is an example of rolling friction. It's pretty good CGI too for the time. Anyway, that's not rolling friction, but sliding friction for the one spinning. All right, so fluid friction is the next one. Fluid friction is anything. Remember, air is a fluid, liquids are a fluid. Fluid friction is anything that can split that fluid apart, or when that happens, you create friction. So space shuttle coming in for a landing has to have heat shields because there's so much friction from the atmosphere as it comes through. So here is fluid friction. And these are air jumpers. There are a couple planes worth of skydivers, and they're going to try and do a formation, and they use fluid friction to speed up and slow down. So when they want to speed up, they pull their arms in and they point their head down, reducing the surface area. And when they want to slow down, then they go back and spread their arms out and their legs into kind of like an X form, trying to get more surface area to use that to control their speed. And you can see this yellow one was pretty flat, and others were going head down. Oh, there he goes, a little head down to try and get caught up, and they're trying to form a huge design in the sky. And you'll notice that there's different colors, and the one in the center, that orange jumpsuit person, is going to be the one that actually gives them the code to release, because not everybody could let go at one time. They needed to get farther apart, so if their parachutes, they can get far enough apart so their parachutes wouldn't intertwine. And when he's looking at his altimeter, he will start kicking to make people let go. And they're still trying to get this formation going, trying to get their design going. And they don't do it on the first time. They're actually going to have to jump for a second time to try it. And they're coming in to get really close. So watching, the reds are trying to come in. They're actually starting to release. They kicked again. Now the next wave are going to go. He kicked again. Now all the red suits are going to go. A few of the yellows are going to go. Kicked again. Now all the yellows are gone. Kicked again. Now there goes the green. And I have a feeling if I try and jump forward, this is going to stall out. But we can try. On the second attempt, they get much closer to getting the nice formation. If this doesn't play all the way through, you can, see, it's going to stop. You can Google that and it will come up. So I want you to take a look at this picture and tell me, what types of friction do you think this picture within a 30-second span was experiencing? Well, don't you think the motorcycle had rolling friction before it flipped? Don't you think that the motorcycle seat right now is experiencing some sliding friction as it slides across the ground? And the guy flying through the air is splitting the fluids apart, so that would be your fluid friction. So within 30 seconds, we had rolling, sliding, and fluid. And sadly, shortly, the motorcyclist is going to experience some sliding friction too. What kind of friction is this person using? Well, they're using fluid friction. This dog is going to experience what kind of friction? Well, if you said sliding friction, you got it. This dog loves to go on the slide. My sister's dog, when they had the hill at their front yard, he would slide down the hill until he created almost a luge, and he'd go up and down the hill. He loved to slide. So it's funny to see because he actually carries his sled back up to get another round, and he's experiencing sliding friction. All right, what kind of friction? Well, they're falling through the air, so that would be fluid friction, but I'm guessing that at some point they were on a surfboard, which would also be gliding through the water, which is also, guess what? Fluid friction. Again, here's a surfboard on the top, the crest of the wave, and that would be fluid friction. And I believe this, if I remember correctly, is Barracuda, but let's see if I'm right. Yep. This is a school of Barracuda. And they experience, obviously, fluid friction as they move through the water. All right. When you get a chance, and we'll get to the end of this, you're going to want to go through, and you're going to want to fill in these questions. So you need to finish the Ed puzzle, and then you need to come back and do these. So really what we're talking about is fill in the blank. Friction occurs when an object moves through a fluid. You should know that would be fluid friction. So use the options available to you. These are pictures. Again, if you see a swoosh mark, that's indicating motion. So this would be a leaf fluttering through the air. That is a fluid friction, right? Car on wheels is going to be a rolling friction. If you're pushing something on a flat surface, that would be sliding friction. This is in the water. This is on skates. So some of these, like if you said, on number 6, you're probably going to say sliding friction, although technically the skates technically melt the surface, and the water molecules act like little ball bearings, so you could technically be correct with fluid friction or rolling friction for that, but that has to do with some thermodynamics of the skate. A ball flying through the air, wheels on a skateboard, this is going through the air. This is a ball rolling down. You're talking fluid, you're talking rolling, or you're talking sliding friction. You need to identify which part's what. And this is the ostrich feather and the bowling ball. And this is that vacuum chamber that they tested some of the rockets that went up into space. So it's a huge chamber. You're talking many, many feet, like 6, 8, 10 feet thick walls to be able to survive atmospheric pressure, not to cave it. But you'll notice the ostrich feather and that bowling ball are going to hit at exactly the same time. In the absence of fluid friction, everything on Earth falls at 9.8 meters per second squared. So after 1 second, you'd be traveling 10 meters per second. After 3 seconds, you'd be traveling 30 meters per second. After 10 seconds, you'd be traveling at 100 meters per second. In the absence of fluid friction, air resistance, we don't have a terminal velocity when we are in free fall and we have gravity pulling us down. And remember, other planets have different gravitational pulls, so they have different rates at which you'd fall. We are 9.8 meters per second squared. And that's the end of these notes. So now when we're done, I need you to go into the actual notes, answer those questions, because there will be questions like that on the test, so this is good practice. If, as always, you need help, ask.